Today we're looking at lesson 2.05, Twin Powers. So today's objective is I can correctly evaluate an exponential expression with a negative exponent in 2 out of 2 problems. So in the previous lesson we were looking at fraction exponents. Today we're going to look at negative exponents. So more exponent rules, hooray! We've done a few of these before. These are the ones we've covered before. So they may look familiar, but this is a good one to put in your notes if you don't have it there already. These are the 4 we've covered. So when we're multiplying exponential expressions, we can add the exponents. When we're dividing exponential expressions, we can subtract the exponents. We can multiply over parentheses. So we multiply the exponents over parentheses. And then the most recent one we did in the last lesson was this one, where the denominator of the exponent becomes a root. The numerator stays an exponent. So let's look at some new things here. How do we write these expanded? So we have a times b, that quantity cubed. How do we expand that? Well, we know what a cube means. We're just going to multiply it 3 times. So we have a times b times a times b times a times b. Right? 3 times. 1, 2, 3. Well, now we have multiplication between all of these. We have multiply, 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 multiply. That's really the only operation that's happening here. So multiply everywhere. And there's a property of multiplication called the commutative property that means we can actually multiply in any order and we'll come out with the same answer. So I'm going to drop these parentheses and reorder these. And I'm going to write all the a's together, a times a times a, and then write all the b's together, b times b times b. Well, if we simplify those now, we consolidate that notation. This will just be a to the 3rd times b to the 3rd. So what we demonstrated there is that this exponent of a 3, can actually distribute over multiplication. If we're multiplying inside the parentheses, we can say, well, this is a to the 3rd times b to the 3rd, like that. Let's see if we can do the same thing with division. We're going to expand this out the same way, so this is going to be a over b times a over b times a over b. Right, we just multiplied that same thing 3 times. Well, when we're multiplying fractions, we multiply across the numerator and across the denominator. So we get a times a times a on top, and b times b times b on the bottom. Once again, we can simplify that notation and call this a to the 3rd over b to the 3rd. So yeah, it did work. We can distribute this exponent over division. So this can be generalized by these rules right here. That's just saying we can distribute the exponent over multiplication and over division. All right, let's look at a few more exponent rules. We're going to try simplifying this, a to the 3rd over a to the 3rd, with 2 different methods. The first one we're going to do is we're going to apply this division rule we've made before. So a to the 3rd over a to the 3rd equals, well, this is going to be 3 minus 3, a to the 3 minus 3, which is a to the 0. Our second method is we will expand them out, so a times a, and then try canceling them and see what we get left over. So we started out with a to the 3rd over a to the 3rd. When we expand these, we get a times a times a over a times a times a. Now we know that we can cancel in fractions when we have the same number multiplied, so Those a's will cancel, those a's will cancel, and those a's will cancel. What are we left with? In fractions, it might be easy to forget that we have something left. We can think, do we have 1 left? Do we have 0 left? I'm not sure. But we can remember we can multiply anything by 1. So there's still a 1 on top and a 1 on bottom here. So this just simplifies to 1 over 1, which is 1. Now we've talked about this a to the 0 before. We've said it was just defined as 1. We just kind of stated that. But now we've actually demonstrated that a to the 0 is 1, just by using different rules on the same expression. So a to the 0 is 1. We've demonstrated it. Let's look at a similar one with slightly different numbers. Now we're going to do a to the 3rd over a to the 4th. Same methods, a to the 3rd over a to the 4th. This will be a to the 3 minus 4. We use that same rule, numerator minus denominator, exponents. We get a to the negative 1. Now we're going to expand and cancel. So a to the 3rd over a to the 4th, we start at the same place. On the top we will have a times a times a. On the bottom we will have a times a times a times a, 4 of them. Remember there's an invisible 1 here. So these a's will cancel, a, and what's left is just 1 over a. So that seems to indicate that a to the negative 1 is the same thing as 1 over a. Let's do one more of these. A to the 3rd over a to the 5th. So we're going to use this rule again, and we're going to get a to the 3 minus 5. We subtract the exponents. 3 minus 5 is negative 2, so this is going to be a to the negative 2. Now let's try expanding and canceling. We start at the same place, a to the 3rd over a to the 5th. This is a times a times a over a times a times a times a times a. And we can have an invisible 1 there. These a's will cancel, these a's will cancel, these a's will cancel. Looks like we're left with 2 a's on the bottom. So that'll be 1 over a squared. A times a is a squared. So now this seems to indicate that a to the negative 2 is the same thing as 1 over a squared. So when we see a negative exponent, that means we put this whole expression in the bottom of a fraction and then make the exponent positive. So here's how we generalize those 2 rules we just looked at. A to the 0 is 1. And we've been using that one for a while, but now we see how we got it. And then a to the negative m is the same thing as 1 over a to the n. You see a negative exponent, we're going to put that expression on the bottom of a fraction with a positive exponent. So here are all 4 that we came up with today. This is a good slide to take a picture of for your notes. 4 more laws of exponents that we're looking at today. Well, that we just looked at today. Distribution over parentheses in 2 cases. A of 0 and then negative, or a to the 0 and then a negative exponent. Today we're going to be focusing on these 2 in particular and see what negative exponents kind of look like and do. So let's take a look at the graph of 2 to the x. We've been looking at this for a while. We know this is an exponential function. It's a curve, so this is all expected. But let's focus on negative values for just a second, where x is negative. What do you notice about the graph where x values are negative? What's happening here? Well, it looks like the y values are getting smaller, right? They're going down, but they're getting closer and closer and closer to 0, but they don't seem to ever quite go negative. It's like there's a line right here that they never cross. So they're getting smaller, but they're never going negative. So this has a term, a vocabulary term in math. We call this an asymptote. And an asymptote is when a function approaches a line but never quite reaches it. So the line it would be approaching here is this x-axis. The x-axis is a line. We could also call that y equals 0, right? Because that's where our y value is 0. So we have an asymptote at y equals 0. The function is approaching it, but it never quite gets to 0 and it never quite crosses it. Asymptotes can also be vertical. We won't be looking at any vertical asymptotes today, but just so you know, that is also a possibility. So let's take a look at the table for this function we just looked at, 2 to the x. We know that 2 to the 4th is 16. We can put that in our calculator. We can calculate it 2, 4, 6, 8, 16. So 2 to the 4th is 16, then 2 to the 3rd is 8. 2 squared is 4, yep, we know that. 2 to the 1st is 2, and we've already stated that anything to the 0 is 1. So what's the pattern here? Notice our x values are going down this time. This is different than we usually write it because we're focusing on negative values today. So as our x values go down, what's our pattern in our y values? 16 to 8, well, it looks like we're multiplying by a half. That's the same thing as dividing by 2. Multiplying by a half, multiplying by a half, multiplying by a half. So if we continue this pattern, what happens? 1 times a half is 1 half. 1 half times 1 half is going to be 1 over 2 times 2, so 1 over 4. We multiply by a half again, we're going to get 1 over 8. And if we multiply by a half another time, we're going to get 1 over 16. Now we don't always know how to visualize fractions or understand what they're saying, so I like to turn these into decimals when we're looking for patterns. 1 half is the same thing as 0.5. 1 quarter is the same thing as 0.25. 1/8 is 0.125. And 1/16 is 0.0625. So now looking at those decimals, what is happening as our x values get more and more and more negative? What's happening to these numbers? Well, it looks like they're getting smaller, right? 0.5, then 0.25, then 0.125. 0.0625 is very small, and we're going to cut that in half on our next step, so it's going to get even smaller. So they're getting very small. Very small. But question, are they ever going to go negative? Will this value ever become negative if we keep multiplying by 1 half? Well, we know that a positive times a positive is a positive. So we'll get a positive, we'll multiply it by a positive again, get a positive, we'll get a positive, we'll get a positive. So no, this is never going to go negative. It's just going to keep coming back smaller and smaller positive numbers. So it will never go negative. And if we remind ourselves what the graph looked like, a couple back here, that makes sense. As our x values go more and more and more negative, the y values got smaller and smaller and smaller and smaller, but never went negative. They never crossed this line. All right. So that makes sense for 2 to the x. How about let's look at 1/2 to the x. We want to compare and contrast 2 to the x and 1/2 to the x. How are they the same? How are they different? Let's look at them side by side. We have 2 to the x over here, 1/2 to the x over here. What do we notice is the same? What do we notice is different? Well, they look like they're the same shape, just flipped over a line, right? They look like they're mirror images. This one's going up while this one's going down. So one goes up and one goes down. Do they have the same asymptote? This line that they approach? So this is at y equals 0. This one also has an asymptote over here at y equals 0. So yeah, they have the same asymptote, but they're going opposite directions on it. So same asymptote, but they're approaching from different directions. What else can we notice? How about the y-intercept? Is the y-intercept the same or different? Has the same y-intercept. So clearly these functions must be related some way, right? They have a lot in common. Why do we suppose these might be related in this way? Let's look into it a little bit more. So let's fill in this table now. This is our second function we've looked at, 1/2 to the x. And we're going to use this rule we came up with earlier, where we can distribute the exponent. So our first one is 1/2 to the 4th. We're going to distribute the exponent and get 1 to the 4th over 2 to the 4th. 1 to any power is just 1, and then 2 to the 4th is 16. So this is 1 over 16. If we do this with 3, we can see that 1/2 to the 3rd is going to be 1 to the 3rd over 2 to the 3rd, which is 1 over 8. If we square it, this will be 1 squared over 2 squared, which is 1 over 4. We know that anything to the 1 power is just itself. Anything to the 0 power is 1. So what is our pattern here? What's happening? We can't always tell quite as well with fractions. But maybe let's try multiplying by 2. Now once again, we're going down because we're focusing on negative values here. So we're counting down by x. We're multiplying by 2 at each step, so the denominator cuts in half. Right, so if you have 1 over 16 times 2, you'll get 2 over 16, which reduces to 1 over 8. So that's why we're multiplying by 2 here. Multiply by 2, multiply by 2. So if we keep this pattern up, what's our next number? 1 times 2 is 2. 2 times 2 is 4. And we keep counting up. 8, oops, multiply by 2, and we get 16. So now, as our x values are going more and more negative, what's happening to our y values? What's happening here? Our next one would be 32. So now as x is going more negative, our y values are growing, and they're growing really fast. Let's relate this back to the graph and make sure that makes sense. So here's our graph of 1/2 to the x. We said as x values go negative, so over here, as these x values go negative, our y values get really big, really fast. So that is what's happening on the graph. They're growing very quickly, they're going up super fast. So it does match. All right, so we filled out a table for both of these functions. What if we put them side by side? Do you see a pattern here? What do you notice about these two functions side by side? Well, you may notice that they're flipped. It looks like they're just going exactly in the opposite order. So this goes from 16, cuts in half all the way down to 1/16. So it starts at 1/16 and multiplies by 2 all the way up to 16. So they're exactly the same, they're just reversed. Another thing you might notice is if you look down this way, the values are flipped upside down. So this is 16, this is 1/16. This is 8, this is 1/8. 4, 1/4. And it works over here as well. 1/2, if you flip this upside down, that'll be 2. 1/4, flip it upside down, that's 4/1, right? That just is 4. 1/8 is 8/1, or is flipped upside down, 8/1. So they're reversed order, and at any particular input, they're also upside down. And we have a fancy word for that. We call those inverses. Upside down just means it's inverse. So now if we look back at our graph, these are those two functions over the top of each other. We can think of these as twin functions. They mirror each other. They have the same values, but they're going opposite directions. Now looking at these two functions, 1/2 to the x and 2 to the x, why would you think these are twin functions like that? Does that make sense if we do negative values over here and negative and positive values over here, that they'll be reversed like that? This is a fraction. I'm not sure I would see that. But maybe we can use some of our rules of exponents to write this function a different way and it'll become clearer. Can we think of another way to write that function using these rules? Well, let's see. We know that we can distribute the exponent, right? So let's try that. So we have 1/2 to the x. We can distribute that exponent. We'll get 1 to the x over 2 to the x. We know that 1 to any exponent is just 1, so that'll be 1/2 to the x. Oh, but this follows this pattern, right? So this is actually 1/2 to the x is the same thing as 2 to the negative x. So 1/2 to the x, 1/2 to the x is the same thing as 2 to the negative x. If we look back up here and we write that instead, y equals 2 to the negative x, these are the same function. Now can you see why these might be reversed? This is 2 to the negative x, this is 2 to the positive x. So as we flip the x values, it has a twin value on the other side for that positive or negative x. This one has positive x's, this one has negative x's. So that's why they're twin functions. It's because of this, the nature of this negative exponent means we're going to turn it into a fraction. So that is everything for today. I can correctly evaluate an exponential expression with a negative exponent in 2 out of 2 problems.